Hi everyone, I'm Anish and this is Lab 1 Constant Velocity. So in this video I'll go over the introduction, so the purpose of our lab, some formulas that we used, our experiment and our data that we got, the glow script I wrote and the model it generated, and a discussion of possible errors and if it followed Newton's second law. So our purpose of this lab is to measure the one-dimensional motion of an object moving at a constant speed without changing direction. We will use Tracker to create an experimental model to and compare it to a theoretical model created by GlowScript. So our object is a cart on rails. And then our observed position is being measured by Tracker, and then our predicted position is being measured by GlowScript. So two things we'll have to visit first before we get into the lab is Newton's first and second law. So Newton's first law says that if the net external force on an object is zero, the object will keep on doing what it's doing. So if it's at rest, it'll stay at rest. If it's moving, it'll keep on moving in a straight line. Newton's second law says the net force of an object equals its mass times its acceleration, F equals ma. So the object accelerates in the direction of the net force, and the acceleration gets smaller if the mass gets bigger. We'll also have to use these four formulas. We have to use the velocity update formula, which is the most important one in my opinion. We have to use the average velocity formula, the position update formula, and Newton's second law. The velocity update formula basically says that if the net force acting on the system is zero, then the velocity does not change. So we have to use that and plug it into our position update formula and our velocity, essentially. So our experimental procedure, what we did for this experiment was I first recorded the object traveling at a constant speed on a frictionless surface, rails, so friction is pretty negligible here. I uploaded this video to Tracker to track the object center of mass frame by frame. You can see that these red diamonds equal the center of masses, as it moves along. I'll create an experimental model using the center of mass data versus time, the frames that we have. I'll use the starter code on GlowScript to create a theoretical model with some values that I get from the Tracker data, and then I'll input the values from Tracker into GlowScript and create an Excel chart to compare the two models. So this is our experiment. Our system is the object on rails, and our surrounding is everything else, including air resistance. So that was our experiment. So our tracker data shows that this is our tracker data basically, and the graph shows a almost linear line, but it's not linear, of course, because of human error, but we'll revisit that later. And we just want to compare that to the theoretical model we make with GlowScript. So our tracker data says our initial position is this, and then the total time it took for this entire experiment is 4.3 seconds, and we'll get the initial velocity from the changes in position from the first two frames. And then we do that, and then we get this as our initial velocity, and we need to input this into our velocity update formula later. So here is the GlowScript code that I wrote. I first set my net force to 0, and then I plugged in the initial velocity and position from my tracker data. Then I set delta t to 0.33 because the total time it took was 4.3 seconds over a total of 130 frames. And then I set mass will not affect my velocity in the velocity update here. And then I created the position update formula to predict my position, basically. So here's the results I got. The tracker shows a almost close linear pattern, and then the GlowScript shows a completely linear pattern. And putting it on top of each other, it follows the theoretical model pretty closely, my tracker data. So what are some sources of error that could cause this variation? So we have air resistance at first because air is pushing and slowing the object down, which is why there's a kind of curves down here. It slows down on the ascent. And then we have human error. So of course I'm going to make some mistakes when I put the center of masses in the tracking data. So some discussion, what if the axes were flipped? If the axes were flipped, then the slope would be negative, but everything else would be essentially the same. The position and time graphs would also be the same. And if F net equals 0, that means all the forces add up to 0. That means momentum is constant. On the y-axis, the normal force and weight force will be canceled out. And in the x-axis, the friction is very small and can be balanced by a small push we did in the beginning. This keeps the object moving at a nearly constant velocity. Thank you. And our models show that the Newton's second law was supported